Thank you everybody for assisting, and thank you for inviting me to this session. It's really an honor for me to present my work. So I am currently a PhD student at EDF R&D, so the energy provider in France. I cannot make it smaller up. Okay. And I'm currently doing a PhD in conjunction with Aix-Marseille University on the use of textual data for time series forecasting. So if you have any question, don't hesitate to ask me during this presentation. So first, I will give you a bit of background and motivation behind this PhD thesis. So despite being extremely accurate with around 1% of relative error, the operation models at EDF sometimes make significant errors, especially during particular periods like the COVID-19 pandemic or during strikes, since they include only calendar information, and so they don't have any social component for the forecasting. And while ubiquitous, textual information are not yet used in forecasting models, especially for energy time series related problems, despite the relevant information they could have. And only few elements in literature exist that are cited here, but they mostly focus on financial time series. And also another problem we might have at EDF is how to make forecasts when meteorological information like temperature or wind speed, for instance, are missing, or because it's also expensive. Sometimes it would be preferable to do a forecast without them. And so all these 3 points motivate my work. So in the first part, I will discuss about weather reports for national load demand prediction. To be more precise, the data we are working with is the French national load that you can see here between 2007 and 2018. And when working with electricity demand, models use calendar and meteorological information. For instance, one very important feature is the time of the year, which is 0. So what you see here is the load depending on the time of the year, where 0 corresponds to the early January, the middle corresponds to summer like June or July, and here it corresponds to the end of the year like December. And so you can see that in winter, the consumption is much higher than it is in summer. Another important feature, of course, is the temperature one, with high consumption being for cold temperatures, because in France, the heating systems is heavily reliant on electricity. And then it goes down, but then increases again because of a cooling effect. So with AC typically. And so what we will try to do is see what happens if we use instead daily weather reports from Météo France, which is the French meteorological organization. To give you an idea, these weather reports have a bit like what I presented here on my screen. This is a British one, but the idea is the same. They describe the weather in a general fashion, with emphasis on the temperature, on the raindrops, on the wind, and so on. And what we will see is that they still have relevant information which can be used especially for the meteorological part of models. And also one final point is that what I present is for French data, but we also conducted experiments for UK data with very similar results. So the first point you have to do when using text data is to encode it numerically. And among different representations, what we kept are the TF-IDF one, which means term frequency inverse document frequency, where the TF-IDF score for a word W in document D is equal to its frequency of the word W in the document D times a penalization, which will basically penalize words that are too frequent in the corpus. And so, for instance, if you have a word which is very specific to document D, its TF-IDF score in it will be high. But if the word is present in every document of the corpus, then its TF-IDF score will be low. Another encoding we considered is a neural word embedding, where each word is represented by a vector. Here, each line corresponds to a different word, and this representation is obtained by training a neural network on the task of electricity load forecasting. So it yields a representation which is very tailored to a problem. So to summarize it, our pipeline is the following. First, we have the raw text that we encode numerically, either TF-IDF or with word embedding. Then we have a machine learning model, either a random forest or neural network, depending on the encoding, which will take the encoded text and also eventually traditional calendar and meteorological data. In the end, we obtain as output the forecast for the electricity demand. And so here I present the results we obtained on 2.5 years, going from 2016 to 2018. What you see here is, for instance, a model which would here TOY corresponds to the time of the year, and DOW corresponds to a day of the week. And so this model corresponds to a situation where we don't have access to a temperature. And you can see that for this model, the error is extremely high, with almost 5,000 megawatts of root mean squared error. And what happens is when you use a text, you drop the error by almost 2,000 points, which will mean that the text really gives information about meteorological information like the temperature. And here, this line corresponds to a model using temperature as well as smooth temperature, and you can see that its error is still lower than the model using the text, which is because the textual information is more fuzzy and less precise than numerical information. And so it means that a model using only text will not be able to beat, of course, a model using real numerical temperature. But what's interesting is that when you include the text with the temperature information, which corresponds to this line, we can enhance the model even further. So we gain like more than 100 megawatts of root mean squared error, which is not bad. And finally, what we also want to do, because I didn't mention it, but these are midterm models. If we want to go to short-term models, which are basically day-ahead models, what we can do is apply an ARIMA correction, so basic time series models, which enhance the models even further. And again, the model using textual information yields the best results. And statistically speaking, all the improvements brought by text are significant when using, for instance, a Diebold-Mariano test yielding a p-value less than 1%. And I'd mentioned also data imputation, and our approach can be used for data imputation with success. We'll perhaps go a bit further to this slide. So basically what we did is to generate in temperature, so this is for temperature, we generated missing values in our data set. And we compared our approach using text with benchmarks like the last observation carried forward in green, and the Kalman filtering, which is very popular for missing data imputation, in red. And what you see here is basically numbers of consecutive missing days of data and of different error metrics, which are the root mean squared error and the R2 coefficient. And what we see is that approach using text yields the best result, no matter how many missing days are present in the data set. And what's very interesting is that our method has like a threshold, asymptotic threshold of error, which makes it very useful when big chunks of data are missing. which is basically almost the case when working with large databases of meteorological data. And also what's interesting with our approach is that it's interpretable, because what we can see, for instance, when using a random forest based on TF-IDF features, is that the words selected by the forest are relevant since they are calendar or words mentioning if it's cold, whether cold or hot. Like, for instance, you can see that the days of the week or the month have very high importance. Words like snow, freezing, sleet, wintry, frost, warm, which all are relevant to temperature and thus to the load demand are naturally selected. And so it's very reassuring to see that our approach yields spontaneously natural interpretation. And this is also the case for neural networks, actually, since if we represent our word embedding in 2 dimensions using, for instance, TSNE representation, what we can see in this embedding space is that the words increasing and decreasing the electricity demand are basically opposed in this embedding space. For instance, here in blue, you have all the cold words, so increasing the load, and red and orange, you have rather the warm words, so decreasing the load. And even if it's a projection, basically they are opposed in the space. So this was our first part dealing with weather reports for forecasting. And now I will also talk about Twitter data for specifically forecasting during the COVID-19 lockdown. Because as I mentioned, our models at EDF use calendar and meteorological information, and so they lack of social information, which can be brought by social media like Twitter. And especially during the COVID lockdowns, there was no way for them to know what was happening. And it is also other applications that I will mention in conclusion. So what I did is to include in correction models frequency of keywords such as teleworking or childcare correction models. So we will use our midterm models. And then apply a correction to rectify the forecast for the COVID-19 lockdown in France. So to show you a bit why we were motivated to do that, here we can see in black the national demand, in red the frequency of the mention of teleworking on French Twitter. And what you can see here is that basically the shape of the frequency has the shape of epidemic waves, which will have an impact on the demand. And this is why we chose, for instance, this keyword. So our midterm model is a GAM, generalized additive model, which decomposes the load into a sum of different effects, which are calendar, so day of the week, time of the year, as well as temperature and smooth temperature. What we do then is to train a 1 day ahead short-term correction model, which will take as input the GAM and also the Twitter word frequency to output a correction. And finally, the final forecast is obtained by summing the GAM and the correction, which is here a random forest prediction. And so what you can see here, for instance, in black is the residuals, so the error of the midterm model, which is negatively correlated with the frequency of teleworking information from Twitter. So this again motivates the use of this approach to correct the demand forecast. And finally, here what we can see is the result evaluated for 3 different models on 3 different periods. So pre-COVID data, first month of lockdown in France, and then a bit more than the second lockdown of a bit more than 1 month of the first lockdown in France, so from mid-April to early June. For the operational model, a simple correction model and a Twitter correction model, so the one I mentioned earlier. And what you can see basically is that Twitter, even outside of COVID period, brings information, and especially during the 2 lockdown periods, we can see that the improvement brought compared to even a simple correction model is significant. So it's more than 100 megawatts of root mean squared error, for instance, here, and here is a bit the same. And again, our results are significant when using a Diebold Mariano test. So again, they are quite strong. So to summarize a bit the work, we successfully used text data to forecast electricity demand in case of missing meteorological information, and even improve predictions when it is available. We also managed to obtain strong results for the imputation of missing temperature in databases, as we saw it earlier. And finally, Twitter data, so a different type of textual information, can be used for the correction of forecasts during the COVID-19 lockdown in France. And so for the upcoming work, what we did up to now is to emphasize on national demand. And we think that textual data would be even more relevant for local information, for local forecasting, especially during extreme weather drops, for instance. And also another use that we already, for which we already have results, is the use of Twitter for the detection of outages on the network. So again, on a local scale. Thank you for your attention.
Thank you very much, David. Any question for David?
I think I didn't see the discussion.
No. Okay, so
if you do, if you have any questions, don't hesitate to ask me. I will be present to answer them.
So I have a question.
Okay.
So first of all, thank you for this interesting job. It's kind of another view for forecasting by combining different kind of data. So can I ask why didn't use the state-of-art NLP techniques based on like a transformer like T5 Roberta or BERT, etc.? Is there any special reason for that?
We actually use them. For instance, BERT, we tried it last year and yielded actually poor results. So for instance, I don't remember exactly the error metrics, but it was significantly above what we could obtain with, for instance, TF-IDF. And our supposition is that it's because for training a transformer or BERT, like the state-of-the-art models, you need a huge amount of data sets. And so we have a basis of more than 4,000 days. And so we guess it's not enough to achieve a good training for such models, for instance.
Got it. So for your case, simpler model works better. Okay.
Exactly, yeah.
Any other question? Anyway, you have the time really to connect together later if you want, really.
Yeah.
Larry,
okay, well, thank you.
Yeah. Thank you very much, David. Larry?
Yes.
So where are you? Oh,
David, give me access to share. Or can you? It's still disabled.
where I don't see your just ready.
Is David the host now?
Am I the host? So I will try to give you, and I cannot see your name actually.
It's Lawrence Danston.
Yeah, I'm trying to pass it, but there's so many.
Lawrence.
I cannot find you in the list, damn it. 1 second, 1 second. Can I?
I don't believe you need to be the host to share the screen.
Can you now?
Let me try again. 1 second. Yes.
Awesome.
Okay. Yeah. Good.
Good. Excellent. All right. Well, good evening, good afternoon, good morning, wherever you are. I'm Larry Vanston. I'm flying under two banners today. I've spent most of my career working for Technology Futures, where we do technology forecasting for commercial purposes. And this year we launched a nonprofit called TFI Projects, which is more aimed at using forecasts for saving the world, so to speak. And so I'm still involved with both, but this is probably closer to saving the world. So I'm flying under the TFI Projects flag. The other thing I want to point out is that I've slightly changed the title for cultural sensitivity purposes. Now we'll be working for the machine learning boss. As I indicated, I've spent most of my life doing technology forecasting in the commercial space, and mostly for in communications. And in that role, I've spent a lot of time forecasting how one technology substitutes for another. For example, fiber versus copper, wireless for wireline, digital for analog. Also spent a lot of time forecasting performance improvement in technology. So in data rate improvement for communications, spectral efficiency, for example, in communications. And then I've also looked a lot at the drivers and constraints for technology adoption that are important. A couple of years ago, I started thinking about how technology forecasting might apply to the adoption of artificial intelligence, machine learning, and then especially in general, but also especially in forecasting. And so I've not done an official forecast per se, but I have given it some thought and came up with a conceptual, intuitive paradigm for looking at basically AI, machine learning in particular, as a technological substitution, replacing or at least supplementing statistical forecasting. And I've pretty much come to the conclusion that that's what we're experiencing. And I'll give you a little bit more of a background on why I think that. Then what I'll turn to assuming that, what does it mean for us? And generally, when you have a technology substitution, there are winners and there are losers. And it's often the people in the old technology that are the losers, which should maybe concern some of us. Except I think this is a special case where actually there's probably many, many more opportunities for people in the old technology due to this transition than there are threats. And that's why my title says we'll thrive. And then what I will end on is what I call the imperative of relevance. We have so many important problems in the world now. Many of them involve forecasts in the future. We have these powerful new tools that have so much potential. I think it's our responsibility to remain relevant and to adopt them where appropriate to help solve these problems. So I mentioned technology substitution. When we're forecasting these things, we often don't have much data. We're often trying to forecast early in the adoption. But regardless of that, we often see a pattern like shown in the blue curve here of the new technology gaining market share over time. And often for these major technology substitutions, we're talking about years or decades. This particular example has a substitution completing in about a decade. And there are different models, different contingencies that will affect this, but this is sort of the general idea that I carry around in my head all the time and have for decades now. The blue line is the new technology. The market share for the old technology, of course, is the inverse of that. And so that declines over time. And generally what we find is the new technology slowly penetrates the market as it improves. and eventually it improves to the extent that it begins to take over the market very rapidly. Where are we on this pattern now with forecasting? I think a pretty good threshold for when we started was probably the 2018. If you went to the ISF in Denver, in Boulder, Colorado, that year, you'll recall there were several good, outstanding presentations on machine learning applied to forecasting. That was the year that a mixed machine learning model won the M4 competition. So we were just barely getting started on that process. If you look at this year at ISF, I think we have 7 sessions on machine learning and specific to machine learning. And then in other sessions, there's plenty of other instances of talks about using machine learning for forecasting. So I'm going to estimate here in 2021, we're probably at maybe 10 or 15% adoption, according to that simple, very simplified, intuitive metric. So if it follows a typical S-shaped curve, sometime in the middle of the decade, we'll be at about 50% machine learning versus traditional statistical methods, and perhaps by the end of the decade, we'll be done. Food for thought, at least. In terms of performance, which we look at a lot, it's hard to define, one metric to measure AI performance. And it varies from field to field. Even within forecasting, it probably varies. And I don't have one particular statistic to show you. In some past presentations I made, I've dug into it a little bit. But just let's say that machine learning and forecasting is definitely improving in performance. It's probably some type of exponential improvement curve. I don't think we're approaching any type of limit at this point in it, at least in general terms. One kind of very informal way to look at it is that, early in this improvement, say the M3 competition, machine learning did not do well at all. By the time we got to M4, we were up further up one of these curves, and machine learning sort of broke even for the first time. And then for M5, we saw that machine learning totally dominated the competition. So that would be kind of an indication of one of these curves. So we have a situation where both we think that it's being adopted as well as rapidly improving and will continue to improve. Now, I mentioned drivers and constraints. This is what we habitually do when we're trying to assess where a technology is headed vis-a-vis the old technology. And I'm just going to jump into the drivers for machine learning forecasting. For one thing, it's a generalized versus specialized tool. So we take advantage in forecasting of all the progress that's made in machine learning in general. And so that's a driver. Of course, we're making rapid technological progress. The availability of large data sets now, huge increases in computer power are all drivers. But I think for this substitution, perhaps the most important one is that machine learning and particularly neural networks can theoretically model anything or practically anything. If you look at the universal approximation theorems, they kind of get at that point. If you think about a single node in a neural network, essentially the equivalent of a multiple regression, which is probably the most advanced statistical most business people, for example, ever know. And by being able to model nonlinearities, to be able to model any logical function, either or, you can build models now theoretically that can essentially do anything, which is essentially headroom that's crazy. If you compare that with where we are with classical forecasting, it's kind of amazing. And then the advantage that we've just begun to tap is being able to unify non-numeric data, including images and text. So I was very interested in David's excellent presentation just before mine, was showing an example of this. And I think maybe Artemos may have some examples on the image side of this. So again, lots of headroom for this new technology. Constraints, of course, there are lots of constraints. Computer intensive, large data requirements, overfitting, instability, not always the most accurate. The problem with the black box, ML's lack of insight, and of course, forecasters aren't as familiar with it. My belief is all these constraints can be overcome and are being overcome. If you look through the machine learning abstracts in this very conference, you'll see many instances where the authors are referring to what they're doing to overcome one of these constraints. So the other thing I like to point out is constraints are often where the opportunities lie in a new technology, because if you can help address a constraint in a winning technology and push it over the top, so to speak, there'll be rewards for that. So kind of summing up what I've said so far, we're in a classic technology forecast, at least in substitution, where we have an old and new technology. The new technology is improving very rapidly, especially compared to the existing technology. We're not approaching any fundamental limits, and the constraints are likely to be overcome. So, I mean, obviously we could talk a lot about that, but if you assume that for the time being to go forward, then what's the impact? And here, again, I'm going to totally oversimplify because I know nobody really falls completely into one of these categories. But I think for practitioners, what you'll see is ML being more and more embedded in the systems that you use every day, with more and more automation as time goes on. And it'll be behind the scenes, and you won't give a whole lot of thought to it. What it'll mean, though, is that practitioners will be more productive, can do more and better forecasts in a shorter period of time, which will, in itself is good, but also leave time for more of the other things that make a practitioner successful. For applied academicians, and here I talk about people in vertical fields like energy or the environment or tourism or what have you, I think the real interest is that these systems can capture not interrelationships between variables, potentially causality, non-linearities in the data, again, logical conditions, and become much more capable of modeling complex systems. And with just a few wins in this area, I think all of a sudden that our predictions will get better, our policies, prescriptions could be better, and that gives us more influence and power. For theoretical academicians, I guess this was the field at first I was worried about the most. But then the more I thought about it I think they'll thrive as well. If you were to take the skill set to be a good statistical forecaster and line that up with the skill set of being a good machine learning expert, it's pretty much identical. The language is different. They call it bonnet, we call it a hood, so to speak, but it's a very similar skill set. If you dig into the AI literature at all, the problems are super interesting. Fundamental problems that and issues that just are kind of would be hard to resist. And whatever happens to statistics and forecasting, statistics aren't going away by any means. In fact, our need for statistics is increasing. So I think for theoretical academicians, we're in good shape too. I'd like to finish by going back to this imperative of relevance. Again, we live in a problem-rich world. Some of the problems like the climate change and food are critical to mankind. Others are very important to economies, like for tourism, for example. And all of a sudden, we have these new tools that have all sorts of they're not perfect, but they have this insane potential. And I think we'd be wrong, not to seize them and improve them and use them and blend them into what we're doing already. And just looking at again the abstracts of this conference and what I've heard so far, we're well on the way to doing that. So I'm very, very hopeful that my title about thriving is apt. And just one example I just wanted to bring to your attention, just because it's coming up in just a few days, is that the ITU program called AI for Good that I've been keeping track of it for a few years, is having a special session on applying artificial intelligence to climate science. And to the extent that there's forecasters that are involved in artificial intelligence, and that there's a forecasting component to AI, of course, this may be an opportunity for us as a profession to get some traction in an area where, as forecasters, we have not been able to get traction before. So just a thought. In conclusion, I'm really optimistic about where we're going and about this big change. I mentioned TFI projects. What we're all about is independent research and insight into the big issues of our times, which is another reason why I'm kind of excited about the potential for AI and machine learning, and why I think we'll thrive under our new ML boss. Thanks for your attention. If there's time for questions, I'll be happy to take them, or discussions. Otherwise, we can move on.
Yeah, we have still some minutes for questions. Any question?
Well, it's a difficult topic to discuss online. I hope we have a chance sometime to discuss it.
Absolutely. Absolutely, I think, really. So, David, let's move to Petrus' presentation, please.
Okay, 1 second.
Yeah, please. Thank you. Larry, thank you very much for your presentation.
I think it should be good now. Petrus, can you?
Yes, thank you. So I'm actually presenting a paper. It's work with my PhD student, Stuart Royden Turner, who should actually be presenting. And I got an email from him saying that he's just joined us. Stuart, can you just tell us if you are here actually? Otherwise, I'll just start. Okay, Mohsen, I'm going to start, and when Stuart joins us, he can just take over.
Please.
Okay, so I guess you're able to see my slide?
Yeah.
Okay, so the topic of this project is to use machine learning to build a sentiment analysis tool for risk appetite. So the idea behind risk appetite is it's used in investment management. And we got the idea because Stuart actually during his master's dissertation was working on topics of investment management and portfolio management for kind of alternative universe investments. And of course, with the vast amount of text data that is available, this was just a logical topic to tackle. So just to overview, so the paper on the dissertation looks at the economic underpinnings of the project. We're using natural language processing in various ways with alternative data sources. These data sources are very large. And then we're using sentiment modeling using natural language processing. And we've got some preliminary results and analysis. So these were absolutely huge data sets. And I see that Stuart has joined us. So Stuart, you're welcome to just take over.
Hey there, thanks. Sorry about that. Nothing like connectivity issues late in the day. Thanks, Petrus. So yeah, just carrying on, so getting on the large databases, we started to investigate, firstly, many different ways to look at the sentiment modeling from different angles. I'll take you through those different methods. And then finally looking at how we actually extract this into a more meaningful framework for the use case of investment management. So I think we'll just click to the next slide. Okay, so to start again, so just in terms of the framework, what we're really looking at is the objective is to try and describe the use case for useful modeling to investigate alternative data with the use of machine learning techniques in portfolio management or using it for tactical tilts in the investment management framework. So if you look at the sort of schematic on the right, we'd say that a portfolio manager would want to consider different risk premia. So how does he aim to extract value for his investors? That look to ultimately price this and using simulation fit the model to the final client specifications in that kind of ongoing loop. An important step once the portfolio has been set up is the monitoring of the drivers of that value. So what we're saying in this context is sentiment linking through an macroeconomic framework is meaningful, or is it meaningful? And can we identify some of this by using alternative unstructured data through the use of news data and sentiment using Twitter data, alternative social media platforms? So some of the key questions I was thinking of when we set the study up was, can we use this freely available information from news websites, APIs, so it's readily available? Which of these has any power or predictive information that we can use? And does this work well in a combination? So would you be able to look at one news source and then augment that with another set of information with ease? And then another question is making use of machine learning models. Is there a significant benefit? Obviously, having been working in the field for some time, in a practitioner sense, which of these methods are something new and exciting over and above what we would have been traditionally using in a portfolio management setting? So another one is, and I have read a lot of studies around specific use cases for security-based identification, where either Twitter searches are used against a specific security. But now what we're really looking at is these trend-based macroeconomic type analyses and whether there's power in that information set. So some of the design principles for this, I really wanted to make use of free and available information and data. The full design and specification of the data signals. So not using prepackaged sentiment signals. I've seen some great vendor stuff naturally working in the industry. It's already there for you. What I wanted to do was to really test whether using freely available stuff, you could get the stuff together in an amenable fashion. Another thing is when it came to deriving factors or looking for factors, there was no data snooping or correlation analyses beforehand. What I rather said to do was build up an intuition-based logic to build up a factor, and then by all means use it to test it for power. And I can take you through some of those. And I didn't seek to create a whole lot of them. It was really to sort of pluck what I thought were good, solid, grounded factors. And making use of freely available tools, such as Colab, etc. And in Python with Keras. Now, when we look at this sentiment analysis, what we're talking about is to look at unstructured data and to derive some kind of valence or score to describe whether there's positive signals or negative signals in that information set. But as I understood very quickly, you really do need to do a lot of work on that data in the sense of pre-processing to get it in a shape to start to score it. And that is quite a lot of work. First, you've got to break it down by characters, break it into little tokens. Then quite an important step is to join them together. So in some senses, you might want to take words and join them together so that the meaning is retained in the sentence. And also using POS taggers. In this case, I used Python's NLTK to just structure the sentence. This will allow you to use scorers to provide more context when you're looking at the sentence as a whole. Now, when we look at it, this would give us a good grounding to be able to either score that unstructured text, which is now structured, using simple lists, of negative words that would convey negative sentiment. And so therefore you map the words against those negative sentiment signals. Or you could use something slightly more advanced, like in the case of Python's Veda, which would then be more context aware. So once you've scored something using scored a piece of text using lists, then you could also zoom out and look at the context of that word within the sentence to decide, well, if there's a not in front of that word, would that change the sign of the sentiment, and then also we could it scales that sentiment based on other context factors. So we used both of those techniques, and to cut a long story short, very quickly we understood that in the context of the finance domain, VEDA was quite a lot more active in terms of the sentiment scores. So we moved on from there. Could you go to the next slide, please, Petrus? Okay, so now when it comes to actually looking at the data and how we set up that data set and provided that into the training data environment, first of all, there's two primary sources we looked at for this particular display. There was, the main one was Guardian newspaper. We took all that news down, filtered it for the business terms, market and finance sections. By all means, I did have the rest of the data, just it was a lot of noise coming through them. We just simply filtered down for what is practically where I thought the information was linking back to macroeconomics. On the Twitter side, I aim to sort of replicate the same kind of filter criteria that you would be getting. So I found a list of the most prominent economics and market financial profiles on Twitter, and I followed those profiles, as well as used very similar search terms that we used on the Guardian side. For instance, you're looking for interest rates, looking for market shocks, defaults, liquidity crisis. What I definitely didn't do was include anything to do with coronavirus and pandemic, given you'll see later that that's part of the test or validation data set, and I didn't want to have that in the data as a primary search factor. So what we're actually doing is, in terms of the target variable, the sentiment indices that I'm interested in, which are good, I use the OECD database because that allows me to move across countries and pull out similarly set up indices, which is handy, especially if you're looking at it from a global investing perspective. You'd want a consistent set of indices, where in the States they have very good indices like the Michigan University indices, but they're not available everywhere. So this was a consistent one. And we'll, in a later slide, I'll show you the 3 primary indices and just take you through why we're going to, in this analysis, target the one. So now on the training and test data, we looked at it. The data was from 2000, the year 2000 onwards. We used 68% of it, the first 68% of the months in the training, which got us to 2014, and then through to February 2021. It was 2/3 needed to round up to 68%, because in the CARAS framework, you couldn't have a prime number in terms of setting the data up, which just happened to be the case when it was set at 66.7. So I just rounded up to 68% and it worked fine. So now, lastly on the slide, when it comes to factors, simple based factors, we're primarily basing them off the VEDA scores. Now, just a small point, at this point, I did try and train machine learning models directly from the data set, well, the cleaned data set and stemmed data set against the sentiment indices, and it had no power whatsoever. To the degree we're even segmenting it into positive and negative signals, and even at different levels. So to try and identify the 2 crises independently, that just didn't work. It didn't train very well, and it didn't score very well, even on all the newspaper articles or limited parts of it, or even using preliminary filters to filter out something that might have been more targeted just for interest's sake when I saw it fail. So what I moved on to swiftly was then using the actual VEDA data itself. Those factors, as I said, one of them was an R index, which searched for terms like recession, defaults, and liquidity crisis, and used that information in a setting. The other one was simple things like rolling volatility. And then lastly, also the top 75th percentile of VEDA scores. To my mind, I was thinking, if the most positive people turn negative in a time series, that could be some kind of indicator. That actually proved to be true, which we'll see later. And then again, just the final one was the VEDA score. Thank you. We could go to the next slide. So this is the set of models that I looked at. So firstly, lexical models or term frequency and bag of words models. I don't display the results here, but certainly they were in the analysis. A lot to do with the lexical techniques. I found them to be quite handy. Spoken about TextBlob and VEDA. Lastly, the machine learning techniques were the simple ones. Firstly, naive Bayes, support vector, KNN, even went into topic generative models such as LDA, which there are thoughts that you could create good subject identification through time. And then the suite of deep learning machine models, which included the simple neural network models, and also ultimately the LSTM models. Now, just looking at the training data, or the target variables and the sentiment indices, you see that there are 3 there together. The one that I chose for this analysis, which I thought could be quite interesting, is the CLI, sorry, the orange line, which has a very deep drawdown when it comes to the pandemic, the recent pandemic. So the financial crisis would have been in the training data, and this recent crisis would have been outside of the training data. And it's quite interesting because the financial crisis is one born from the financials, and then it moved into the real world, i.e. would have hit the newspapers in that sense too, and sentiment. Whereas the other one was more a human crisis, which naturally would walk into the, into the financial disasters too, or financial strains. So it'd be interesting to see how these models perform respectively. I just, for the sakes of entertainment, put the LSTM framework up there, the architecture framework with the input and memory and forget cells. But we won't go into the architecture now, it's just to illustrate. So thank you, Petrus. Okay, if we could, does this actually allow me to click through? Sorry, Petrus, oh, you got a PDF. Do you mind if I could share my version
Yeah.
where I can click through?
Please do. So Mohsen, you might need to make Stuart a presenter if you don't mind, if he's not. But feel free to take over the slideshow, Stuart.
Thank you. If you, I will need to flip back to the PowerPoint presentation, unfortunately, because this is a set of charts that are overlaid on top of each other.
Yeah.
Well, Moshe, would you mind making me the presenter, please?
David, can you please go back?
Sorry?
David?
Yeah, sorry.
Could you please make me the presenter?
Yeah, but because I'm not the host, it's David.
Well, you cannot see you.
It's Stuart. You need to make Stuart the presenter, please, David.
I am looking for. I cannot find you actually.
It's S. Royden Turner.
Ah, okay. No. Is it good now?
Yes, it is. Thank you. It is allowing me to present.
Thank you.
Okay, so please let me know if you can see my screen.
You're sending us something, but it looks like a completely black screen.
I don't have anything. I have a black screen also.
Yes.
Me too.
Is it coming through now?
Not, yeah, got it. Perfect.
Yeah.
Okay, great. Marvelous. I'm just going to move that out the way. So what I've done is I've set up exactly the same analysis to show you. I incrementally step up through the different models and to show you what the training looks like through the different options that I took. And then lastly, I've repeated the framework for both, firstly with the Guardian data only, and then secondly, I augment the Twitter data and then have a look at the RMSE scores to show you what happened. And I think in time series analysis, I start by looking at the trends and the visuals, just because directionality I think is quite important in this context. So you can see that we got the training data on the right and the test data on the left. You can see that the first, and my labeling has let me down here, sorry, so it's neural network, and that's just a simple RNN is neural network, it's not meant to be RNN. So the first one is, you can see not training or predicting very well. There's the second crisis, which is the pandemic. Not a good feature so far. So if we get through to, then what I've done now is I've said the same model, but I've stepped it up to multi-steps. So 3 months, 90 days. And we're starting to get a little bit of shape that's coming through, but yet not seeing any of the crises or those shock periods. If I then step it to the following model, now I introduce the LSTM framework using a single factor, which is that VEDA data, as well as one training, one time step. And you can see that it is starting to take a little bit of shape and even taking a tiny bit of shape coming into the test set, but still none of them seeing the crisis. If I move forward to then revert back to the neural network model, multivariate with the 3 factors I spoke of, with a single step, it is starting to show a little bit more shape through time, but yet again, still not seeing the crisis. When we move into RNN multivariate and multi-step, you can see that there is a little bit of shape coming into the financial crisis and a little bit of recovery coming out, and not a noticeable difference through the test data set. When we look at the LSTM now, multivariate single step, we can see it's actually starting to track the financial crisis quite well, and it does recover well with some unintended shocks over there or unexpected differences over there. Even in the final training, the final test, you can see towards the more recent data that there is a little bit of volatility in the number, but we could argue that maybe there's a bit of late directional shocks and probably incorrectly directionally moving around. If we move then onto LSTM multivariate, but multi-step, again, 3 months, you can see now that the training data set is starting to predict very, very well. It's starting to become quite accurate and quite sharp. I would propose that, maybe not surprising given autocorrelation in financial markets, but we haven't got any financial data there, just sentiment data so far. So that's quite interesting to me. But when we move into the test data set, it is starting to shape up. It does not see the crisis. Now, what I thought as a last step would be to introduce an ARIMA factor, simple one term of the dependent variable, to say, if I were then using an LSTM model with the knowledge of the sentiment score from last month, what would this prediction look like? And that starts to predict quite well. At 1,000 epochs, it starts to cover this analysis very, very well. You can see now when we move into the test data set, it does start to differ a little bit towards the pandemic. And you can argue that it doesn't see the pandemic until maybe the multi-step kicks as well. But it does eventually shock, and it does give you the depth, and it does recover of the effects of the ARIMA coming through in that modeling. Interesting. I did this analysis both at a rolled up monthly level and at a daily level, where you were holding analysis through the month running towards that T+1. And it had the same in mind. One thing to just keep in mind, this data still has a trading window that I've left 10 days before the end of the month. We don't see any information in this. I thought two things. When we do that, it gives us it allows us from important context to allow them to trade. And then secondly, I didn't want any information leakage. So finally, if you look at the different scores just here, you can see the test data. But well, when I've introduced the Twitter to the analysis, you see that Twitter information doesn't actually improve the information, what the predictability. It simply sets up noise, which I found very interesting. We didn't get any better information from it. I'm just looking at the time. So looking at it, some of the things that I'd like to suggest some of the findings that readily available information, especially with New York Times, which I've looked at too. I just haven't illustrated in this data. Is very easy to work with and it's accessible. Twitter data, I really did want that to be meaningful and have lots of information. It's a lot of hard work to get that data moving, and if anything, we'd need a longer data history, but that's quite an expensive exercise. Models, I found the use of LSTM suited very, very well to this time series modeling. Hybrid techniques and expert judgments from domain perspective were very helpful in this analysis, and I found it very interesting. I have to also just, I was very impressed by the accessibility of tools such as Google's Colab, and as well as the modeling frameworks from
So Stuart might have dropped out. I suppose he was going to say from Keras, which is a free data analysis framework. Are you back, Stuart?
Yes. Can you hear me?
Yeah, we've got you.
Yeah. Did you lose me for a period of time there? Sorry.
You were just, your sound was just gone for a couple of seconds.
Oh, sorry. I was saying towards the end, just when it comes to the tools and the machinery, I was very impressed by the use of, well, Python notebooks for one, with the combination of the Keras API and Google Colab offering very powerful machinery that I'd say has been very helpful for entry-level analysis, and was quite impressive. Yeah, so altogether learned a lot. I'd suggest that in the final part that there is probably a lot of information stored in something like a Twitter database, but you'd need to probably step into the realms of extracting features and having a lot of processes to do that, where that was not the design principle behind this analysis. Thank you.
You finished?
Yes.
Okay. I think you have two in the discussion. You have two questions, I think. One from Shishili, why some forecasts are not smooth and some are smooth. The other question is from the same. You're forecasting horizons. Can you see the discussions?
Sorry, I'm just going to stop sharing so I can't click. Okay, I'm looking for the chat. Oh, yeah. So, okay, first question, why some forecasts are not smooth and some are smooth? So the forecasting horizon, just to answer the first questions, the second question first is one step forward. So it's T+1. We're only forecasting for the next month's sentiment value. Some of them were not smooth, just because of the volatility of the information coming around, and the prediction itself was actually not accurate. I would see the same thing if I used fewer epochs. Even for the accurate models, if you use fewer epochs, it became very, very shaky, and there was quite a lot of noise around that. I think what the most important thing about the smoothness was the moment you included an ARIMA variable, which is this month's, well, your known sentiment value, the modeling itself became very smooth and very accurate, indicating to me that there was a lot of power in that. Knowing what today's sentiment is a very powerful forecasting indicator for tomorrow's sentiment.
Okay.
So yeah, and
question from Inga. How does your prediction compare the naive forecasting? There is quite a bit of a delay. You see it?
So the forecasting that I've shown you here is the stuff that I would say would be classified as the stuff that worked. The naive forecasting, including naive Bayes, let's say a simple linear regression, also looking at a simple bucketing exercise with correlations against both text data as well as the sentiment indices, sorry, the VEDA and text blob data, was not very accurate at all. In fact, they were quite smooth. It didn't have any predictability that I could guess.
Okay.
Question, please. In between, I missed something. So what does it mean for you to speak about multi-step forecasting?
Thank you. So what that meant was that I could take previous time periods of the training data. So it would be T-1 and anything. You could use 6 months in time.
Mm-hmm.
Like,
okay.
I used up to 6 months I fed it back into the Keras framework using 6 time periods prior.
Mm-hmm. Thank you.
Just to add to that too, there was ways you could do that. So either summarize that in the actual data at month end with summarizing prior months, or actually using all the data together in these big rolling windows, which is something unique to those Keras frameworks, which can handle that quite easily. So I didn't test the difference, but it was very easy to do either.
Okay. So thank you very much, Petrus and Stuart, for your excellent presentation. Let's move now with some delay to Artemios' presentation.
Hi.
David?
I hope you can hear me.
David, can
yeah, I'm doing it.
can
Normally
you
you should
give the way
closed.
to Yeah,
it good?
thank you.
Okay, let me check.
Yeah,
Perfect.
good. Thank you.
Can you see like the full screen presentation or not? Just to make
Yeah,
sure.
yeah, yeah. To me, it's okay.
Okay, great. So give me a second. Just so I can introduce myself first. My name is Artemis Amenoglu. I'm a PhD student at the National Technical University of Athens. And basically my area of research is, of course, forecasting, but more specifically, the use of machine learning and deep learning in forecasting. And today I'm going to present you the work we've done together with my colleagues, Dr. Evangelos Pilioti and Professor Vassilios Smakopoulou, which is titled "A Picture is Worth 1,000 Data Points, an image-based time series forecasting approach." So probably you could have guessed from the title that this work is inspired from computer vision. And computer vision is a field where the use of machine learning and deep learning algorithms is a standard practice for many years now. Machine learning and deep learning has been used successfully for years in pattern recognition and content understanding tasks. I'm pretty sure all of you have seen image classification applications distinguishing between cats and dogs, or you've seen semantic segmentation, object detection, and face detection, both in videos and images, and also the more recent headlines about deepfakes and artificial images and how they are generated by machine learning and deep learning algorithms. So basically, the field of computer vision for years has spearheaded the research into deep neural networks. And if someone looks at the some of the landmark neural network architectures, he or she will be able to see the advances in their designs. So, for example, AlexNet was one of the first deep convolutional neural networks. VGG, which came later, basically took the idea of a deep convolutional network and took it even further. ResNet later was able to solve some of the learning issues that the previous models had, and was able to provide an easy way to train an even deeper model. And the same is true for the more recent networks such as DenseNet, Exception, EfficientNet, and the list goes on. So basically, the story of machine learning and computer vision is not the same in forecasting. Forecasting community was rather slow in adopting machine learning as a standard practice. Some poor results in certain applications made the community quite hesitant. And many reasons for that, but some of them probably had to do with the fact that the task of forecasting time series had some unique difficulties, which are not present in other fields, which means that it's more difficult to transfer knowledge from computer vision to forecasting. And also designing ML models requires specialized knowledge that is not always available to practitioners. However, we should mention that in certain industries, ML algorithms were used for forecasting, especially, for example, for demand planning. That picture actually changed after the M4 competition in 2018. Research around machine learning methods increased significantly, and even the more recent M5 competition confirmed the dominance of machine learning methods. The vast majority of submissions there and the top performing methods were actually machine learning, and some of them even deep learning models. And moving to deep learning, actually, sometimes it's quite difficult to distinguish whether an algorithm is machine learning, simply machine learning, or a deep learning algorithm. But without a doubt, some truly deep models have been introduced, claiming significant accuracy. For example, NBITS in 2019 and DeepAR in 2020. Both very accurate models. So all these things motivated us to look into an image-based approach, the documented success of certain deep learning architectures in forecasting tasks, the design practices that we know about and that they come from the field of computer vision, and also the limited number of image-based applications in forecasting. Here I'm mentioning some of them that actually exist. So, for example, forecasting through time series classification, essentially predicting the future trend of a series, combining forecasts by looking at the visual representation of the series, or an image-to-image forecasting applied on financial data, which is the most recent application. So basically, what we wanted to do is to further explore the use of time series imaging in forecasting, and also attempt to develop an end-to-end image-based deep learning model for univariate time series forecasting, which takes images and produces numeric forecasts at the end of the pipeline. So here you can see an overview of the proposed methodology. It consists of 4 discrete steps. Of course, we always begin with the time series that we use for training purposes. We have to pre-process them and create the samples that we are going to use in the second step in order to train our forecasting model. The third step is, of course, to look at the time series that we want to predict. We have to, again, do some pre-processing to them, and then use the previously trained forecasting models, use the pre-processed test series, and then obtain the forecast from the deep learning model. So this is the general overview of the proposed methodology. So now moving on to the first step of the process, which is the time series pre-processing. Here the goal is to essentially transform the time series from the numeric data to the corresponding visual representations. This means going from the 1D numeric vector to a 2D image, essentially. The first step in doing so is to cut the time series into windows of equal size in order for all samples to represent time periods of the same length. If we are talking about the training data set, the training time series, what we do is extract all available windows from all series in order to have more samples to train our models. And if we're talking about the test series, then we only care about the last window, because we only care about getting the forecast from them. In any case, we adjust each window's data points. We use a simple min-max scaling in this case in order for the target range to be from 0 to 1. And then we visualize the data points using a simple line plot. It is important to mention that the images are resized to a 64 by 64 pixels frame, and we use a black and white color scheme in order to reduce the size of the images. Now, before I move on, it is important to mention some of the challenges that we faced and actually guided some of the decisions made above. The first being about storage. In general, storing images takes much more space than storing the corresponding numeric vectors. So that's one thing we should keep in mind. And the second is that in general, if we provide models with larger images, this means that these models, in order to be trained, they require more resources, meaning time, memory, and of course, CPU or GPU processing power. This is the overview of the deep learning model that we employ for this task. Conceptually, it consists of 2 modules, an encoder, which basically transforms the input image to its latent representation. And the second part is the regressor, which takes the latent representation and calculates the forecast that we want. Again, this is just a conceptual schema. In practice, both modules are optimized at the same time as a single neural network. And of course, the one of the great advantages of this approach is that each module, the regression and the encoder, can be implemented using different neural networks. So for example, in this study, we examined 3 encoder variants. A self-designed encoder inspired by ResNet, but developed for this task specifically. VGG19, which is a well-known network from computer vision, and also ResNet 50, that was the third encoder variant that we considered. So getting more into the details of the self-designed encoder and the self-designed network, of course, it is a convolutional network. The building block of it is what we call a convolutional layer, which is actually a series of 3 transformations. The first being a 2D convolution using 3x3 filters with 0 padding, so we make sure that we don't lose any information and our images remain the same size. A bus normalization, and finally a ReLU activation function. So these 3 transformations make up a convolutional layer. Now, 3 of these layers make up a block. And here comes into play the inspiration from ResNet. We introduce an identity shortcut. Basically, the block input is provided at the output of the same block as a shortcut and as a residual connection. And blocks are then organized into stacks. In this specific example, we use 5 stacks of 3 blocks each. And here I should mention that each stack basically reduces the image size by a factor of 2. Usually, in many applications, you do that by using max pooling or average pooling layers. In this specific case, we use a 2D convolution in order to do that because it's more flexible. And also, I should mention that as the stacks go on, so the subsequent stacks have more filters, and the filters are increasing again by a factor of 2. Moving on to the regressor of the architecture. In this case, the regressor essentially is responsible, let's say, for taking the latent representation that was the output of the encoder, and then calculate the forecast from it. In this case, a simple MLP was used as the regressor. It is important to mention that the model provides forecasts for the whole horizon. So we don't have to do a rolling forecast or anything like that. The regressor itself uses 2 fully connected hidden layers, as you can see in the figure. And again, the ReLU activation function was chosen for the hidden layers, the identity function for the output layer, of course. Now, in terms of implementation, all neural networks models were implemented using Python and TensorFlow. And specifically for the case of VGG and ResNet variants, we use the Keras API, which that provides us with ready-to-use pre-trained models, pre-trained on the ImageNet dataset. And what we did is use their parameters as a starting point for training our networks. So a couple of words about the experimental design. The dataset we used is the yearly series of the M4 competition. We wanted a dataset that has enough series to train our models, but not too many that resource demands cannot be met. In this specific case, it has 23,000 series from various domains. And of course, we use the original setup of the M4 competition for our study to be comparable with other studies. This means the forecasting horizon was set to 6 years ahead, and the last 6 observations of each series were used only for evaluation, not for hyperparameter optimization or training. We evaluated the models using 3 forecasting performance measures, SMAPE, MACE, and the OWA. These three are the official accuracy measures of the M4 competition. And again, that's the reason for choosing them to evaluate our models. So let's look at the results of our approach. So the first three rows of the table actually hold the results of some benchmarks. Theta method, which is the most accurate statistical benchmark of the M4 competition. ESRNN proposed by SMIL was the winning submission of the M4 competition and the top performing method in the yearly dataset also. Simple MLP was an MLP benchmark that we used, we developed and used. And the last three rows are the three variants, the self-designed one, the VGG one, and the ResNet one. So as you can see, the self-designed variant is the most accurate method of all. Compared to Theta, the improvements in accuracy are greater than 10%, which is quite significant. But also the probably the most satisfying result is the accuracy improvement over a very competitive method such as ESRNN, which won the competition. There, in comparison to ESRNN, we had more than 1% accuracy improvements. And lastly, from this table, it is quite interesting the fact that the self-designed encoder actually performed better than the variants that used ResNet 50 and VGG 19 as the encoder. Now, in order to make sure that our results are representative and are significant, we ran a multiple comparison with the best tests. Essentially, we look at the ranks of the methods in order to determine whether the improvements that were documented are significant. And as you can see, doesn't matter if we look at the SMAPE or the MACE as the main accuracy measure. You can see that the self-designed network is significantly better than all other benchmarks and variants. And this is important because even you can see that when you have so competitive, so very accurate methods, even the 1% improvement can be a significant improvement if you run such a test. And now to conclude the presentation of our approach. So of course, all three image-based variants provided very accurate forecasts. Even if some of the variants weren't able to beat like the top performing method of the M4, still they provided very accurate forecasts. For the self-designed network, which was specifically tailored for this task, outperforms all other benchmarks. And it is encouraging that existing computer vision models can be used in case someone, for example, doesn't want or doesn't know how to design a more complex encoder for his own needs. In general, if we take into consideration that essentially what we ask from the network is to look at an image and provide us with 6 numbers, it's quite astonishing that we had these results. But of course, the research doesn't stop here because we plan on expanding the research in order to include data sets of series of different frequencies, monthly, quarterly data, and of course from other domains too. We plan to focus more on how to effectively train existing architectures such as VGG, ResNet, or more recent computer vision models for such a task, because we feel like there is great value if we can make them work. And of course, lastly, but not least important, we want to consider more visual representations. So there are ideas about, for example, recurrence plots that can be used as either additional inputs or replacing the single line plots that we used in this specific study. And we believe that we will get even better results by doing that. So this is some of the references that there were throughout this presentation. Thank you. I hope that in the 15 minutes I was able to give you an idea of our approach. And if you have any questions, feel free to ask.
Yeah, thank you very much, really, Artemios. Very excellent presentation. We can take one or two quick questions if you have.
So I have a question. So basically I have two questions. First one is, did you combine with this approach with a normal forecasting techniques? And is there any additional values for adding the image with a combination of classical forecasting? This is my first question. And the second one, like visual attention is also important topic for computer vision. So did you try to introduce a kind of attention network which could be very interesting to check it out, which part of the image has been getting attended for the prediction of the timestamps? So maybe this could be helpful and to ask whether you tested or not.
Okay, I'll start by answering the second question, actually. Okay, we haven't tested such a model yet. This is something that we can most certainly do in the future. But we try to look at basically by looking at the convolutional layers, we are able to identify the areas of the image that take the most of the attention, let's say, by looking at the heat maps of the images. And the beauty of the model is that different filters and different parts of the network look at different parts of the images. So there's not a single specific area that these models looked at and identified as the most significant. Basically, we had some filters that focused on the earlier parts of the series, some of them at the more recent history of the series. So it was all over the place. Now, in regards to the first question, we didn't try to combine this approach with any other approach that uses the numeric data. But from past experience, I would say that if you, for example, combine these forecasts with, I don't know, with ESRNS forecasts or with the MLP we used as a benchmark, probably you would get even better results simply by combining two very competitive forecasting methods.
Okay.
Thank you for answer.
Artemios, thank you very much.
Can I ask one quick question?
We are a little bit late. Please, can you direct your question directly to
Will do.
To Artemios, please? Thank you very much.
You.
I'm so sorry.
Thank you.
Yeah, thank you. The last presentation from Evangelos, please.
He should be already.
David, are you ready? You're good.
He's already ready.
Yes.
Yeah, thank you.
Okay. Okay, I think that you can now see my full screen.
Yeah.
Okay, so I'm Vangelis Piliotis from National Technical University of Athens, and today I'm gonna talk about time series augmentation techniques that can be used to improve the performance of global models and the approaches that we now call, let's say, cross-learning. It's a work that I've done with Artemis and my professor Vassilios Asimapopoulos. So first, before I start discussing about the augmentation, let's define what cross-learning really means. It's about trying to extract knowledge about from multiple time series instead of just looking on a single series that you want to forecast. So cross-learning can take a lot of forms. For example, you might want to simply optimize some parameters based on what works best on a variety of series, or then you can also select an approach that works best for a set of series instead of a single series being forecast. Now, the advantages of using this approach is, first of all, that you can extract and learn common patterns that are observed in a set of time series. So even if the data set is homogeneous, or even if it consists of diverse time series, you can extract a lot of different patterns and based on that generalize your forecasting solution. And a nice side effect of this is that you also tend to avoid overfitting, because if you build a nice global model that looks at different patterns and not focuses on just some particular data points, then you're probably gonna avoid overfitting your model. Then again, it helps you mitigate issues related with data availability. So a standard problem when using machine learning models, and especially neural networks for forecasting a single time series, is that we may run out of data points to effectively train our model. So now we can, with cross-learning techniques, predict both short and long time series. And finally, it reduces computational cost, because you just have to create a single model in order to produce a forecast for multiple time series, instead of having hundreds or thousands of single models to predict this series individually. As I discussed, cross-learning is particularly useful for machine learning, for neural networks that are data hungry in nature. We have seen the value of cross-learning in the recent M competitions, with the most significant contribution being that of SMIL, who introduced a neat approach for learning from multiple time series. Also, almost all of the winning submissions in M5 apply the type of cross-learning, and nowadays cross-learning is considered a standard practice for training machine learning methods, and there's a lot of work done about how we can actually improve this process. Now, the problem is that, of course, if you have a large data set like the M4 competition, or another data set that consists of thousands of millions of series, your model will be able to generalize and be trained effectively. But this won't easily be the case if your data set is small. So data augmentation is a technique that can be used to artificially increase the size of the train set and allow our model to learn better the common patterns observed in the data set. Although these approaches are quite popular in other fields of machine learning, basically mostly in image classification, in speech recognition, the work done in the area of forecasting is limited, especially for when it comes to global forecasting methods, because as we will discuss next, there has been some data augmentation techniques, but mostly for univariate time series forecasting. Now, to start, we'll first describe the experimental setup of this study. In order to be aligned with the previous presentation of Artemis, I'm going to use the 23,000 yearly time series of the M4 competition and use a simple feed-forward neural network to train our model. The hyperparameters of the neural network are listed below, but I don't think that this is a very important. We are going to use the standard look-back window technique in order to train our neural network. So basically for each series, we're going to extract some windows. The first 18 observations of each window will be used as an input, and the 6 last observation would be used as an output window. So basically, we will ask our neural network to predict this part of the series when it has access to the information of the left part of the window. Now, as you can understand, if I have a long enough series, I can either extract a single window, for example, getting the last observations, 24 observations of the time series, or I can get several windows by rolling these windows from the very beginning to the end of the series. So this, for example, in the M4, in the yearly series of the M4 competition, gonna give me about 14,000 samples for the last window approach, and more than 200,000 samples for the several windows approach. Now, since one of the focus of the main focus of the study is how data augmentation can help us when the data set is small, we also consider 3 different data sets: the complete data set, which is the large one, let's say, consisting of 23,000 series. Then we have a medium and a small data set. Of course, the small data set includes all the series of the medium one. The medium data set includes all the series from the small data set, and the large includes all the series from the rest of the data sets. And for reasons of simplicity, I'm going to use the symmetric mean absolute percentage error to report the results, but these are identical for the maze. Now we have 2 baseline global methods. The first one that does not apply augmentation, we have a simple feed-forward neural network and use the last look-back window to train our neural network. The second one is the same, but we use all possible look-back windows to benefit the most out of the data set available. And then we have 5 time series augmentation techniques, some that are well known in the literature and some new ones. The first one is about bootstrapping. The second is about generating time series, adding noise, combining samples, and interpolation. Okay, so this is an overview of the data set examined and how the sample available for training our neural network changes in its implementation. As you can see, when we augment, we basically double the size of the data set. Of course, we can triple or even make this sample 10 times more, but you know, I just want to show you what happens in the most, let's say, simplistic scenario where you just double the train set. Okay, so the first technique is about bootstrapping. We implement bootstrapping like described in the work of Berkmeyer, 2016. We basically apply a Cox transformation to stabilize the variance of the series and convert multiplicative patterns to additive ones. Then we decompose using the STL method into trend, seasonal, and the remainder component. And then we use moving blocks in order to bootstrap the remainder of the series. Finally, we add the bootstrapped in the trend and the seasonal component and inverse the box-box transformation. Okay, so we basically have a series like the black one shown here, and we can create many series like the blue ones. Of course, we can either select a simple look-back windows out of all the series created, or even more out of them. The main advantage of these techniques is that it filters out structural changes and extreme values. Okay, so this is useful. The drawback is that it's quite computationally expensive for implementing in with neural networks that are already quite expensive. So it requires offline computations, and also, as you can remember from the previous picture, the patterns introduced are not really new. Okay, so we do not really include any new information here. And this is why, as you can see here, although by adding a lot of windows from the original data set, I can get improvements over using just the last window, and of course over the theta method, the bootstrapped approach does not work better. Okay, so I double the size and of the train set, and nevertheless I do not get any improvements. Now, another idea is to generate time series. We use the approach proposed by Fotios Petropoulos in 2014. So we basically assume that we can describe any time series using a multiplicative decomposition process of trend, seasonality, and randomness. Okay, so if we assume that we can measure the strength of the trend, the seasonality, and the randomness, we can basically generate as many time series of these particular futures as we want. Okay, so this is how the generation process looks like. We have a trend component. We can add seasonality above the trend and the randomness, and then get a time series like this, and extract as many loopback windows as we want to. This is a generic example. Here with the yearly series, we do not have, of course, the seasonal component. Now, the advantages is that this approach is that we have the ability to introduce a completely new series in our data set that have similar characteristics with the reference data set. The drawbacks again are that they're computationally expensive, and they cannot be, the series cannot be really created online, okay, so while training the neural network. However, we can see that since the information added here is new, this approach does slightly better than the bootstrap approach, okay. In the medium data set, it even does better than the simple MLP approach, but still nothing special. A third option is to add noise to the original windows created. In this example, in order to keep things simple, we just add a uniformly distributed noise of 0.9 to 1.1. The series will look like this. The advantage is, of course, that this approach is very cheap to compute, so you can include it in an online fashion. So, for example, when you insert a batch of time series in your neural network, we can automatically create and double the size of this batch. However, as you can see here, we do not still get any significant improvements, basically because, as you can see in the previous picture, the patterns introduced do not really differ from the original ones. Okay, so it seems that we do have to introduce some new information here to make augmentation really work. So in order to deal with this issue, we're going to another approach, which is about combining loopback windows that are already available in the train set. So we randomly select 2 or 3 or whatever we want, how many we want, loopback windows, and we can use the mean or the median operator to combine the results. Okay, so this is an example of how 2 already available loopback windows can be averaged in order to get a new one. Again, this approach is very cheap to implement, so it can be used on the fly, and the patterns observed and created are quite different in nature compared to the existing ones. The main drawback here is that if you already have a small data set, you cannot really create a lot of new samples. You can, of course, increase your trained sample, but you may just, have the opportunity to create enough samples to make a difference. Another drawback of this approach is that if you start combining a lot of windows together, you will inevitably end up with a very generic pattern of a series that describes the average, let's say, series of your data set. Okay, so you won't diversify a lot, and this is exactly why in this approach we use just we combine just two windows because we want to keep our combinations as diverse as possible. Okay, and as you can see here, we start getting some improvements both for the small and the large data set. Now, another approach is what we call the interpolating of samples. We basically start by looking at any possible window we have already created. We zoom in a particular part of this window. Okay, so we get this subsequence here, and then we start interpolating between, putting additional points using linear interpolation between all those points in order to get our final result. The main benefit of this approach is that you can just focus on very particular parts of the series where there's a different pattern compared to the complete window you initially had created, and based on that, start creating look-back windows that are significantly different than the original ones. Again, this approach is computational cheap. So again, we applied it in an online fashion, okay, while training the neural network. No need to do any pre-processing offline. As I discussed, the patterns are quite original compared to the initial train set. And here you can see the improvements we get over the rest of the approaches, which are quite significant. Now, the only drawback of this approach is probably that, like the combinations, the number of the samples that you can augment are, again, limited and depend on the initial size of your train set. Okay, this is a summary of the results in a percentage form. This shows the percentage improvement over the benchmark model that uses all the loopback windows. Okay, so like we discussed, the bootstrap, the generator, all have a negative effect. Again, the noise does not really work, but when we start to combine loopback windows, and especially if we start to interpolate windows, we get some notable improvements, especially for the smaller data set that has most need for looking at more data in order to be effectively trained. These are some multiple comparisons with the best tests. Okay, so here you can see that the interpolation approach works best in all data sets. Due to the sample size, of course, these differences may not always be considered significant, but when the data set is quite large, you can clearly see that we get some significance of results. So in order to conclude, we find from this study that when we already have large data sets, augmentation is probably optional and may not always lead to significant improvements. However, it is highly recommended for smaller data sets. We also find that in order for augmentation to work, we have to think of smart ways in order for the augmentation to lead to the creation of diverse patterns that represent the series being forecast. We also see that traditional time-consuming techniques like the bootstrapping approach and the time series of generation techniques should be replaced by other more computational cheap approaches that are easy to be applied in an online fashion. Of course, we want to expand this study not only in the direction of thinking of more ways of applying data augmentation, but also seeing if these results stand for different sizes, frequencies, characteristics, and of series, and also depending on, let's say, the homogeneity of the data sets. So that's all from me.
Thank you very much, really, Evangelos, for your interesting, really presentation. We can take one question, very quick question, because we are really delayed. Sorry for this.
No, it's okay. I'm open to questions for anyone interested.
Yeah. In any case, everybody can really direct any question to really Evangelos by discussion, chat, and so on. Really, I would like to really all the presenters, all the presentation here. Thank you very much. As I said to you, please don't forget to vote for the best student presentation. Here we had really Artemios presentation. You have to make your choice about with different presentation. The second thing, please do not forget really to post your presentation on the website or IAF site when you will be invited. I think in mid-July, please. And I have a personal really message with Spiros Makridakis. I have the honor really to co-author together a book about the forecasting with AI. See the theme. It is not really the final point. So I will be very happy to welcome any presentation, any paper for publication. I will send to many of our colleagues within the IAF invitation and explanation about the process and everything. We say by end of July. Yeah.
A lot of what you just said, we could not understand, or at least I could not understand. So if you said something that we need to know about, you might want to send a text message or something.
Yes. Yeah. So anyway, I will send really to many of the really colleagues and researcher students who are working on the AI really topic, really invitation possibility paper for that. And we are expecting to really publish this mid to 22 or September. So again, thank you for your passion. Thank you for presentations, and have a good evening and a good day for the US citizens and so on. Thank you.
Thank you,
Thank you a lot. Goodbye.
Bye-bye.